So I'm going to start off by asking a question. So if I look at units of measurement and I said meters, for example, meters measures length, right? So does kilometers, so does yards. Degrees Celsius measures heat, so does degrees Fahrenheit, so does Kelvin. So there are different measurement units which measure the same thing, whether it's length, distance, or temperature, or weight, or whatever else. What does degrees measure? Say that again? Angles. What does that mean? What is an angle? Yeah, that's not bad. For the video, that was Sam saying a proportion of a circle. Degrees or angles measure an amount of turn. Unlike distance, which goes from one spot to another, when you measure an angle, like Horatio was measuring angles or Cuddles was measuring an angle, both Horatio and Cuddles were standing on a spot, weren't they? And the measurement of turn was from, say for elevation and depression, was from the horizon and either up or down, like so. But the person or the cat stayed on the one spot. And it's the turning of the head, either upways or downways, was the measurement of angle. That's what angle does, it measures turn. Or if I'm standing on the spot and I'm facing forwards in the class and then I turn to face the door, I haven't moved, but we can say I've turned 90 degrees. So it's a measurement of turn. And what we're going to do in the first part of this lesson is we're going to be introduced to a new angle of measurement called radians. Okay? And I'm really glad Sam mentioned about something to do with circles, because it does feel very much linked together, doesn't it? The idea of when you turn around you're turning in a circle in a way. So let me just get it up onto the screen. And make for a good pause in the video, won't it? What we have here is a circle. Hooray. Remember how yesterday we were talking about trig ratios and like if it's a right angle triangle with a 30-degree angle in the corner, then you can make that triangle big or small, but they are similar triangles, they're proportionally the same. It's a pretty low bar of understanding, I think, to say that all circles are proportionally the same, right? Make a circle big or make a circle small, proportionally they're the same because it's just the one shape for a circle. So I've got a circle here and I have made it a specific radius of 1 unit length. Doesn't matter whether it's centimetre, metre, kilometre, yard or foot, it's just 1 unit of length. Okay, this is called the unit circle, and it's a concept we're going to use over and over again in our trigonometry section. So this is the unit circle. So, who can remember what the formula is for the circumference of any circle? You're mixing two formulas there. You've mixed the circumference and the area formula together there. 2 pi r. Yep. So the circumference of any circle is 2 pi r. 2 times pi times r, or pi d. But in this case, we've got the radius here, so 2 pi r. So for the unit circle, what is the circumference? Just 2 pi, right? Just 2 pi. So the unit circle circumference doesn't have, well, has an invisible radius value, I suppose, so it's just 1. So we end up with a circumference of 2 pi. So what we can do is we can start talking about a measurement of turn as being a fraction of the circumference of a circle. Now I'm going to zoom out and you're going to see some stuff I haven't got to yet. Just because I want to respect that you have got some prior learning coming into here, just raise your hands if you've come across radians before. I don't know what you've seen in Maths Extended. No, this is new for everyone. No, except for a couple. You've seen it, Callum? I think so. Yeah, and Sam, I would have expected you to have seen it. Okay, cool. So just, you tell me if I'm going too slowly for you, Callum, but everyone else, I reckon you probably need that. So this new measurement of turn, this new angle measurement is called radians. So now I'm on slide 2 there. And it's a fraction or a proportion of the circumference of the unit circle. That's how it's defined. It's just a definition, right? Just like, why is a yard the length it is? Why is a metre the length it is? It's because some human beings got together and said, let's make it this length. You know, it's in a sense it's arbitrary, but it has some thinking behind it. And similarly for mathematicians or scientists, they were looking for a different angle measurement other than degrees, because 360 degrees is good for a number of reasons. But this radian measurement makes sense for a lot of other different reasons, which I won't go through. And that is why we use it, I suppose. But you don't have to know the history lesson behind it. You just need to know that it's a different way of measuring the same thing as degrees does. And there's some good reasons behind it, which I won't go into. So it's a fraction or proportion of the unit circle. So 360 degrees would be, if I started here and I'm pointing in the same direction as the radius line, 360 would be going all the way around until I'm facing the same direction again, right? So in other words, if I'm looking at Hunter and I do a 360, then I'll be looking at Hunter again, right? So 360 degrees. Well, on the unit circle, that would be like going all the way around to the start again, so that would be the full circumference. So 360 degrees is 2 pi. Does that make sense? The full circumference. 180 degrees is what? Half that? So guess what 180 degrees is in radians? Pi. Yep, pi. Half of it. Does that make sense so far? Okay, what about 90 degrees? Yeah, half pi, or pi on 2. And what about 0 degrees? 0. Okay? So these are the radian equivalents. Now, radians are a little bit special in mathematics in that we know that almost always, when we're talking about a measurement, we have to have some sort of unit there. So we use the little superscript O for degrees, for example. We use cm for centimetres, etc. Radians, we don't normally write in the units. So if I'm working in radians, I'm working in, I don't put a unit after it, I don't put rads. Some old textbooks might put a little C like this, because it's a circular measurement of angle. So that's why they have C there, but not usually. You might see me use it once in a while if I have to really distinguish between degrees and radians, but I wouldn't normally do it. Okay, so it's unit, the unit is radians, but we don't normally write something in for that. All right, good so far? Okay, so it's a proportion of the unit circle. So I'm going to it's a really, really brief explanation as to how we calculate, how we convert from one to the other. But honestly, it's not that hard. So I'll do it really quickly. So if I'm looking at a proportion of the unit circle, then if the amount of degrees is theta, then I'm going to divide it by 360 to get it as a fraction of 360. So let's look at 90 degrees as an example. If it's a proportion of the unit circle, then 90 degrees as a proportion of 360 will be 90 over 360, right? So I'm always going to divide the angle by 360, and then I'm going to multiply it by 2 pi over 1, just 2 pi. So this says this is the fraction, and it's a fraction of 2 pi, which is the full circle. So effectively 2 pi is the full rotation or the full turn in radians, and 360 is the full turn in degrees. So basically, I'm sort of multiplying by 2 pi and then dividing by 360. Is that okay so far? You don't have to learn this bit. The bit in red is the bit you're going to learn. Well, since I'll always be dividing by 360 and multiplying by 2 pi, there's a really simple cancel down here, because 2 goes into itself once and goes into 360 180 times. I'm just halving it there. So I've got theta over 180 multiplied by pi over 1. Okay? So I've just cancelled down a little bit, but a slightly easier way of writing that is theta multiplied by pi over 180. Okay, so that bit in red is the rule that you need to be able to use. Theta in degrees multiplied by pi over 180. Let's see it in practice. If I have 10 degrees and I want to put it in radians, I go 10 multiplied by pi over 180. 10 goes into 180 18 times. So I've got pi over 18, and I'm done. So 10 degrees is equal to pi on 18 in radians. It's the same measurement of turn. It's like that much of a turn, 18 to the pi. Yep, is that okay? Just tell me if I'm going too fast or too slow. Degrees to radians degrees are going to be exactly the opposite. I have used a little C there so you can sort of see it. It's exactly the same logic. So if you understood the logic before, it's the same. I'm going to take the radian measurement and divide it by 2 pi, and then I'm going to multiply it by 360, and I just put it over 1 so that it's a fraction and a fraction. Oops. And always, 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 the 2 will cancel into 180. And so I'm left with the rule. If I can just go straight to the rule, I'm going to have the conversion from radians to degrees as theta times 180 over pi. And that's the conversion back. Is that okay? So I'll flip between screens so you can sort of see them there. Bottom left, theta times pi on 180 to go from degrees to radians. And then theta times 180 on pi to go from radians to degrees. So it's just the flipping of that, then you're multiplying theta by. And there's an example up there, which I've done already, but I'll just erase so you can sort of see it from scratch. So we've got pi on 6 is equal to pi on 6 times 180 on pi. So the pi's will cancel out. 6 goes into 18 3 times, so it goes into 180 30 times. And so it equals 30 degrees. And that's the radian to degrees. Any questions on that? Okay. Let's have a look at an angle of 6. What would I multiply 6 by to convert it into the other angle measurement? Would I multiply it by 180 on pi, or would I multiply it by pi on 180? So would I use this one? That's multiplying it by pi on 180. Or would I use this one? Multiplying it by 180 on pi. Let's just do a straw poll. Who thinks I should multiply it by, what's the other one? Pi on 180. Who thinks I, 2, 3, 4, 3.5. Okay, who thinks I should multiply it by 180 on pi? 1, 2, 3, 4. 4 and 4, there are 12 in this class. Sam's on his own journey, so let's say that's 4, 8, 3 people were too emotionally compromised by this to make a decision one way or the other. It's a hard world out there, guys. If you can't decide on this, we're in all sorts of bother. Which one is correct? This one's correct. Because this does not have the degree symbol. Now, one of the traps for young players with radians is that you can assume, excuse me, you can assume that if it doesn't have pi in it, it must be degrees. It's got to have the degree symbol. If it doesn't, it's radians. And that's why I even got a diagram there for you. You know that pi is about 3.14 something, right? You should know that. So 2 pi is about 6.2, nearly 6.3. Okay? So an angle of 6, as you can see here, would be almost an entire rotation, but not quite. It's just below 2 pi. So the trap for young players is always make sure you understand what unit you're starting with. Okay? If it says there was an angle of 1, and it doesn't say degrees, then that means 1 radians. Okay? It often won't say that this is a radian measurement. Okay, so it would actually be 180 on pi to convert it from, if you wanted to convert it from one to the other. It's a radian, and yeah, it would be converted into degrees. Okay, that's all I'm going to say. I'm going to pause for a moment. I think this is a fairly straightforward process. I want to give you a really short opportunity to practice some really common angles. You should be able to do any angle, but the 7 on the screen, I'll zoom up with, I think. The 7 on the screen here are ones I want you to try. 1, 2, 3, and 4, you can pretty well much just use the conversion factors that I told you before. I'll put it up on the whiteboard so you can see them. But for 5, 6, and 7, although you can use the conversion formulas that I gave you, maybe there's a smarter or more efficient way of solving these problems. I'll let you think about that. So obviously, I hope it makes sense. I'm asking you to convert from whatever it was into the alternate unit. Okay, I'll pause the video, have a go at doing them. Right, so here we go. This is really just a, did you get the right answers rather than me going through the whole process. So 270 degrees is equal to 3 pi on 2. I'll tell you a fast way of doing it. I didn't put a pointer down for this one, but a faster way of looking at it, remember that degrees and gradients, they operate in a similar fashion. So if you know that 270 is 3 lots of 90, well, if pi on 2 is 1 lot of 90, then 270 must be 3 lots of pi on 2, or 3 pi on 2. Okay, and that's the more efficient way of looking at some of these, is to consider what they mean in relation to other angles that you do know. 45 degrees. Well, I know that 45 degrees is half of 90 degrees, and if 90 degrees is pi on 2, then 45 degrees must be a half of pi on 2, which is pi on 4. See what I mean? Now, I was expecting you to just use the formula. I wanted you to practice it. So don't get me wrong, the formula definitely works, but sometimes a bit of nous works as well to make it more efficient for you to solve these problems. 30 degrees is going to be a third of 90 degrees. So it's pi on 6. There you go. Pi on 3 is twice pi on 6, so that's got to be 60 degrees. Okay? Again, just use the formulas. I wasn't expecting you to see these lengths. All of these lengths are really fast if your fraction work is pretty good. And if your fraction work still sucks at year 11, then good news is you can always remediate that if you want to. It just requires perseverance and effort, and it will pay dividends in this unit. There's a lot of fraction stuff in this unit. But you need to make me aware that you want extra resources on that. 2 pi on 3, you could use the conversion technique, or you could see that 2 pi on 3 is 2 times pi on 3, which we just worked out. So it must be 120 degrees. See what I mean? It's a little bit of thinking first, and you can get there a little bit faster. 5 pi on 4 is, well, that's 4 pi on 4 plus pi on 4. 4 pi on 4 is pi, which is 180. and pi on 4 is 45, so that must be 225 degrees. Does that make sense? So just stepping back a moment and looking at them might give you shortcuts to these things. 75 degrees was the hardest one to do. I mean, you can do it longhand, straightforward, that's fine, using the formula. 75 degrees, can anyone see the split for that one? See, each of these ones here, I've kind of split it up. 45 and 30, that'll do. Won't it? Which is better than what I told you to do, wasn't it, Hunter? So that's pi on 4 plus pi on 6. Common factor of 12, so that's 3 pi. You do this in your head, I'm just doing it so we can see the process here. Plus 2 pi on 12, so that's 5 pi on 12. There we go. Done. So there are some shortcuts you can take if you know some basic angles. And that's why, not in today's lesson, but perhaps when we get a little bit closer to doing stuff on functions, I'm actually going to spend some time with you working on coming up with a table of common radian to degree conversions. I can't, can you show me that? I think the information sheet might have them. Oh, yeah, cool. So on your information sheet, you're given some of these common radians measurements, and so knowing what they are automatically in your head, pi on 6, 30, pi on 3, 60, etc., knowing that, and then knowing that you can sort of combine them together to come up with things like 125 and whatever else is really quite useful. So yeah, but we'll come up with our own chart so that you've got something to refer to while you're still practicing. Okay, so that's it for radian measure. The last part of this unit I want to talk about for this lesson, is the sine rule, which I gave everyone a worksheet for. I'm just going to stop this video here because it's all about radians and record a brand new video for sine rule. So if you haven't got that sheet from the front, can you come and grab it now and then have a seat while I switch over?